This is a recast of the 7,300-word piece, Neural Architecture Search, NAS, from Schneepat.com. This article is about neural architecture search, NAS, a field in machine learning research that focuses on automating the design of neural network architectures. NAS aims to find optimal architectures by exploring a vast search space and employs techniques like reinforcement learning, evolutionary algorithms, and Bayesian optimization. NAS has gained attention for its ability to accelerate the development of neural networks, surpass human-designed networks, and automate the design process. However, there are challenges such as computational costs, limited interpretability, and the need for standardization and evaluation metrics. NAS has applications in various domains like computer vision and natural language processing and holds promise for improving the accuracy and performance of deep learning models. Let's listen in.
Today we'll be talking about neural architecture search, NAS, a field in machine learning research that focuses on automating the design of neural network architectures. Traditionally, designing neural architectures require human expertise and trial and error processes, but NAS provides a promising avenue for automating this task and efficiently discovering high-performing neural network models.
That's right. NAS aims to find the optimal architecture of a neural network by exploring a vast search space of potential architectures. It's like an optimization problem, where the goal is to find the network architecture that maximizes a certain performance metric, such as accuracy or computational efficiency. NAS employs machine learning techniques like reinforcement learning, evolutionary algorithms, or Bayesian optimization to automatically discover the best neural network structure.
And NAS has gained significant attention in recent years because it accelerates the development of neural networks, reducing the need for human experts and manual trial and error processes. It can even find architectures that surpass human-designed networks in terms of performance and efficiency.
Absolutely. The importance and relevance of NAS in modern machine learning research cannot be overstated. It plays a crucial role in automating the design of neural networks, saving time, effort, and resources. Traditional manual design of neural networks has often led to suboptimal solutions, but NAS uses algorithms to automatically search for the best architectures.
NAS also allows researchers to explore a vast design space that would be difficult to comprehend manually. By incorporating techniques like reinforcement learning and evolutionary algorithms, NAS can efficiently explore and exploit the architectural space, resulting in improved performance and greater accuracy in machine learning models.
That's true. And NAS becomes even more relevant in the context of deep learning, where the need for more complex and specialized architectures is growing. NAS enables researchers to tackle complex problems by automatically designing networks that are tailored to specific tasks.
Exactly. NAS is a vital tool in modern machine learning research and has the potential to revolutionize the field by accelerating the development of more efficient and effective neural networks.
Another approach to NAS is the use of reinforcement learning algorithms. Reinforcement learning focuses on training agents to make a sequence of decisions in an environment to maximize a reward signal. In the context of NAS, reinforcement learning algorithms can train an agent to make decisions about the architecture of a neural network.
The agent receives a reward signal based on the performance of the neural network on a particular task and uses this signal to update its parameters and improve its decision-making process. This approach has been shown to be effective in finding optimal neural network architectures for various tasks and is computationally efficient compared to other methods.
However, it's important to note that reinforcement learning algorithms for NAS can be computationally intensive and may require a large amount of computational resources to train.
That's a good point. The computational aspect is definitely something that researchers need to consider when using reinforcement learning for NAS.
Absolutely. NAS has shown promising results in various domains, including image classification, object detection, and natural language processing. It's an exciting field with immense potential for automating and optimizing the design of neural network architectures.
Well said. We've covered the main points of the article, explaining what neural architecture search, NAS, is, why it's important in modern machine learning research, and how reinforcement learning algorithms play a role in NAS. Now let's dive deeper into the evolution of NAS. The article mentions that early efforts in manual architecture design involved experts manually designing architectures based on their deep understanding of the problem domain. They would spend significant amounts of time experimenting with different configurations, using trial and error to arrive at an optimal solution.
That's right. While manual architecture design yielded impressive results in some cases, it was highly time-consuming and labor-intensive. Additionally, the expertise required to manually design architectures limited the accessibility and scalability of this approach. These limitations paved the way for the emergence of automated NAS methods.
Absolutely. With the advent of NAS, the process of designing neural network architectures has been automated. NAS algorithms employ different strategies such as reinforcement learning, evolutionary algorithms, and gradient-based optimization to search and evaluate various network architectures. These methods efficiently explore the vast design space, providing solutions that surpass the performance of manually designed neural networks.
That's a key point. Automated NAS methods address the issue of reproducibility, enabling researchers to perform experiments with different datasets and network configurations. This facilitates comparative studies and advances the field as a whole. The use of automated NAS methods significantly reduces the time and resources required for neural network development, and it has facilitated the creation of sophisticated models that achieve state-of-the-art results in various domains.
Right. And as NAS continues to evolve, it holds immense potential to drive advancements in machine learning and artificial intelligence. The article also mentions the use of evolutionary algorithms and reinforcement learning techniques for NAS.
Evolutionary algorithms simulate the evolution of neural networks by iteratively generating and evaluating candidate architectures based on their performance. This allows for the exploration of a wide range of architectures, resulting in the discovery of novel and effective network structures.
Reinforcement learning algorithms, on the other hand, use trial and error exploration to find optimal architectures through a reward-based learning process. The agent learns to navigate through a search space of possible architectures by receiving rewards or penalties based on the performance of the trained models. This gradually improves its ability to generate higher-performing architectures.
Exactly. However, both evolutionary algorithms and reinforcement learning techniques face challenges in NAS. Selecting appropriate hyperparameters and balancing exploration and exploitation remain challenges in these approaches. Future research efforts will focus on addressing these limitations to further enhance the effectiveness and efficiency of NAS approaches.
And it's worth noting that NAS still faces other challenges, such as the large search space, the high computational cost, and the lack of generalization across different tasks and datasets. But with advancements in machine learning algorithms and computational resources, it is expected that NAS will become an indispensable tool for efficient neural network design in the future.
Absolutely. NAS has already revolutionized the field of deep learning, and it has the potential to drive further advancements and innovations. It's an exciting time for researchers and practitioners in the field.
One of the main techniques used in NAS is reinforcement learning. In reinforcement learning-based approaches, an agent interacts with an environment and learns to improve its performance through a reward system. The agent selects actions, such as adding, removing, or modifying architectural components, based on a policy network that maps states to actions. By optimizing this policy network using reinforcement learning algorithms like Q learning or policy gradients, the agent becomes better at generating high-performing architectures.
That's right. Reinforcement learning-based approaches have shown success in discovering efficient and effective neural architectures in various domains, such as image classification and natural language processing. However, they do come with a drawback: high computational costs. The trial and error iterations involved in reinforcement learning can be time-consuming and resource-intensive.
To address this challenge, researchers have proposed techniques like surrogate models and transfer learning. Surrogate models are approximations of the original model that reduce the computational requirements of the search process. Transfer learning leverages knowledge gained from previous tasks to accelerate the search for optimal architectures. These techniques aim to improve the efficiency of reinforcement learning-based approaches in NAS.
Another technique commonly used in NAS is gradient-based optimization. This approach relies on training a continuous relaxation of the search space, allowing for efficient computation of gradients. By iteratively updating architectural parameters based on these gradients, an optimized architecture can be obtained.
One popular gradient-based method is the reinforcement learning architecture search, our NAS framework. It formulates the search process as a Markov decision process, MDP, and uses a policy network that outputs a distribution over architectural choices. The network is trained using reinforcement learning algorithms like proximal policy optimization, PPO.
Another gradient-based search method is the differentiable architecture search, DARTS approach. DARTS employs a differentiable representation of the architecture and uses gradient descent to optimize the architectural parameters. These gradient-based optimization methods have shown promising results in terms of both efficiency and performance compared to random search methods.
However, gradient-based optimization methods still face challenges. Performance variability and scalability of the search space are areas that require further research and improvements. Researchers are actively working on addressing these challenges to make gradient-based optimization methods even more effective.
Absolutely. And let's not forget about genetic algorithms and evolutionary search, which have also been widely utilized in NAS. These algorithms mimic the principles of natural selection and survival of the fittest. They start with an initial population of random neural architectures and iteratively improve them through mutation, crossover, and selection.
Genetic algorithms explore a vast search space of possible neural architectures and adaptively respond to changing requirements. They can incorporate feedback from the training process to enhance the overall performance of neural networks. By iteratively evolving neural architectures, genetic algorithms provide an effective approach for discovering optimal network configurations.
It's important to note that NAS techniques and algorithms contribute to the success of NAS by efficiently searching for and discovering innovative and high-performing neural network architectures. They help us explore the vast search space and identify optimal architecture designs.
That's right. And with advancements in machine learning algorithms and computational resources, NAS is expected to become an indispensable tool for efficient neural network design in the future.
Indeed, it's an exciting time for researchers and practitioners in the field of deep learning. NAS has already revolutionized the way we design neural networks, and it will continue to drive further advancements and innovations.
Absolutely. One of the main approaches in NAS is random search, which involves randomly sampling architectures from the search space. While this method can potentially find good architectures, it suffers from high computational costs and inefficient exploration of the search space.
That's where Bayesian optimization comes in. It's a more sophisticated technique that uses a surrogate model to approximate the search space and an acquisition function to guide the exploration. By iteratively sampling and updating the surrogate model, Bayesian optimization can adaptively explore the search space and focus on promising regions.
Right. And compared to random search, Bayesian optimization reduces the computational cost and tends to find better architectures. However, the success of Bayesian optimization heavily relies on the choice and optimization of the surrogate model and acquisition function.
That's a crucial point. Careful selection and optimization of these components are necessary for the effectiveness of the NAS algorithm.
Absolutely. Now let's talk about the limitations and challenges of NAS. Firstly, the computational cost associated with searching through a vast space of possible architectures is substantial.
This raises concerns about the scalability of NAS, especially in realistic scenarios where time and resources are limited.
Exactly. Another challenge is the quality and diversity of the search space. If it's limited or lacks representation of important architectural features, NAS may struggle to discover superior neural architectures.
That's true. And the black box nature of the search process often hinders interpretability and understanding of the discovered architectures. This lack of transparency poses challenges in comprehending the inner workings of the models and limits potential improvements or modifications.
Absolutely. While NAS holds great promise, researchers and practitioners must address these challenges and limitations to fully exploit its potential and ensure its practical applicability.
Now, let's move on to the benefits and applications of NAS. One major benefit is its ability to improve the performance and efficiency of neural networks.
That's right. By automating the process of designing neural architectures, NAS can discover optimized network structures that outperform manually designed architectures.
And this is particularly useful in complex tasks such as image and speech recognition, where the design space is vast and conventional methods struggle to find the best architecture.
Absolutely. NAS also offers the potential for domain-specific network design, where architectures can be tailored to specific tasks or datasets.
That's a great point. NAS enables faster and more efficient architecture exploration, saving significant time and computational resources.
And it's not just limited to neural networks. NIS can also be extended to other machine learning algorithms and optimization problems.
Exactly. The benefits and applications of NAS make it a valuable tool for enhancing the performance and efficiency of machine learning systems.
Moving on, NIS has also led to significant advancements in improving the accuracy and performance of deep learning models.
By auditing the process of designing neural architectures, NAS allows for the exploration of a vast space of potential architectures that would be otherwise impossible to manually design and evaluate.
And this not only saves time and effort, but also enables the discovery of novel and highly effective architectures.
NAS has been particularly successful in achieving state-of-the-art results in various fields, such as image classification, object detection, and language modeling.
And by continuously searching for better architectures, NIS has proven to be a powerful tool for pushing the boundaries of deep learning performance.
Absolutely. NAS has greatly contributed to the improved accuracy and performance of deep learning models, making them more capable of tackling complex and real-world problems.
Finally, let's discuss time and resource-efficient model design in NIS. One approach is leveraging previous searches by using surrogate modeling.
This involves building a surrogate model that approximates the performance of different architectures based on their architectural features. Instead of performing an expensive search process for each new architecture, the surrogate model can quickly provide an estimate of its performance.
This significantly reduces the computational resources and time required for architecture search.
Additionally, techniques such as weight sharing and parameter sharing can also be utilized to further improve the efficiency of NAS by reusing weights and parameters across different architectures, reducing the need for redundant computations.
By considering these time and resource-efficient model design techniques, NIS can be made more practical for real-world applications. One important consideration in neural architecture search, NIS, is transfer learning and generalization across datasets. Transfer learning refers to the ability of a model to leverage knowledge gained from one dataset to improve performance on another dataset. This means that a model designed and optimized for one task or dataset can be used as a starting point for another task or dataset. Transfer learning is especially useful when there is limited data available for a specific task. By transferring knowledge from a related task, the model can benefit from the learned representations and reduce the need for extensive training on a new dataset.
Generalization, on the other hand, refers to the ability of a model to perform well on unseen data. It is not just about optimizing for performance on the training data, but also ensuring that the resulting architecture can generalize well to unseen examples. This is crucial for the practical deployment of NAS in real-world applications. We need architectures that can perform well not only on the datasets they were designed for, but also on new and unseen datasets.
NIS has proven to be a powerful tool with applications in various fields, such as computer vision and natural language processing. In computer vision, NIS has been used to automatically discover effective convolutional neural network architectures. NIS algorithms search through a vast space of potential architectures to identify the most optimal and efficient networks for image classification, object detection, and semantic segmentation tasks. This allows for the development of state-of-the-art models in computer vision.
In the field of natural language processing, NAS has shown its potential in automatically designing neural network architectures for tasks like named entity recognition, sentiment analysis, text classification, and machine translation. NAS algorithms in this domain searched through diverse network designs to ensure that the architecture is well suited to process different language structures and achieve high performance. The versatility of NAS allows it to be applied to a wide range of fields, enabling breakthroughs in various domains.
One possible solution to address the computational costs associated with NAS is the use of evolutionary algorithms. These algorithms are inspired by natural selection and aim to find optimal solutions to the iterative process of reproduction, mutation, and selection. In the context of NIS, evolutionary algorithms can be used to generate and evaluate a population of neural architectures. These architectures undergo evolutionary operations such as mutation or crossover to create new architectures. The newly created architectures are then evaluated and selected based on their performance on a given task. This process is repeated for multiple generations until a satisfactory architecture is discovered.
The advantage of using evolutionary algorithms in NAS is their ability to efficiently explore a vast search space. The random mutation and crossover operations allow for the exploration of different architectural configurations, leading to the discovery of potentially novel and high-performing architectures. Furthermore, evolutionary algorithms can be parallelized and distributed across multiple computational resources, further reducing the time required to search for optimal architectures.
Despite its promising potential, NAS also faces several challenges and limitations. One major challenge is the requirement for large computational resources, which can make NAS inaccessible to researchers with limited access to high-performance computing clusters. The time required to search for optimal architectures can also be substantial, hindering the practicality of NAS. Additionally, there's a lack of standardization and evaluation metrics for comparing different NAS algorithms, making it difficult to assess their performance accurately. This limits reproducibility and makes it challenging to build upon existing NAS research.
Another challenge in NAS is constructing an effective search space that contains a diverse range of architectures without overwhelming the algorithm. The quality of the search space greatly affects the performance of NAS algorithms. Lastly, NAS methods are often biased towards larger architectures, which can result in a potential performance cost for resource-constrained environments. These challenges highlight the need for further research and development to address these issues and unlock the full potential of NAS.
Computational complexity and resource requirements are also crucial factors in NAS. Exploring and evaluating a vast search space of potential architectures comes with a significant computational cost. And NAS techniques rely on intensive computational resources to carry out the search process, making computational complexity a key factor in determining the feasibility and efficiency of these approaches. Furthermore, the resource requirements in terms of memory and processing power are essential to consider, especially for larger datasets and more complex models that demand significant resources.
Researchers have explored methods to mitigate the computational cost of NAS, such as using surrogate models to approximate the performance of candidate architectures. Strategies like parameter sharing, weight inheritance, and knowledge distillation have also been proposed to reduce computational burden by reusing information from previously searched architectures. However, computational complexity and resource requirements remain persistent challenges in NAS, and further exploration and optimization are needed for its widespread adoption.
Absolutely. Now, let's move on to another crucial challenge associated with neural architecture search, NAS. The lack of interpretability and human control in architecture design. NAS algorithms are often considered black boxes because they generate complex neural network structures that are difficult to comprehend and interpret. This lack of interpretability restricts designers from understanding the underlying reasoning behind the architecture decisions, making it challenging to troubleshoot and adapt the network design.
That's right. The automated nature of NAS also leaves less room for human intervention and control in the architectural design process. While the goal of NAS is to relieve human experts from the task of handcrafting architectures, it also leads to a loss of creative input and domain expertise. Without human involvement, the development of innovative and specialized network structures that could be essential for solving specific problems or meeting unique requirements may be hindered.
Exactly. Striking a balance between automation and human control is crucial for the success and effectiveness of NAS in architecture design. It's important to find ways to make NAS algorithms more interpretable and allow for human input in the design process, while still leveraging the benefits of automation.
Moving on, overfitting and generalization issues are common challenges faced when dealing with automatically designed architectures in NAS. Overfitting occurs when a model becomes too specialized to the training data and fails to generalize well to new unseen data. This is a significant concern as it limits the usefulness and applicability of the discovered architectures in real-world scenarios.
To address this issue, techniques such as regularization and early stopping are commonly employed. Regularization methods penalize complex architectures, encouraging simpler and more generalizable models. Early stopping monitors the validation loss during training and stops the search process when overfitting starts to occur.
These techniques help ensure that NAS yields architectures that not only perform well in the training set, but also generalize effectively to new data. By carefully considering overfitting and generalization, NAS can produce more practical and reliable architectures for real-world applications.
Now let's talk about the need for robust benchmark datasets and evaluation metrics in NAS. To effectively evaluate and compare the performance of different NAS methods, It's crucial to have benchmark datasets that cover various aspects of the problem domain. These datasets should be diverse, large enough to capture the complexity of the problem and avoid biases.
Absolutely. Additionally, selecting appropriate evaluation metrics is vital for accurately assessing the performance of NAS methods. These metrics should align with the objectives of the problem and provide meaningful insights into the efficacy of the models. For example, classification tasks commonly use metrics like accuracy, precision, recall, and F1 score, while regression problems often use mean squared error, MSE, and root mean squared error, RMSE.
Right, robust benchmark datasets and evaluation metrics enable comprehensive and reliable evaluations of NAS methods, allowing researchers to make informed decisions and advancements in this field.
Lastly, reinforcement learning, RL, has emerged as a popular approach to NAS. RL algorithms train a policy network to make decisions on a sequence of actions to maximize a cumulative reward. In the context of NAS, the policy network represents the architecture search space, and the actions correspond to architectural choices. The reward signal is usually defined as the performance of the searched architecture on a validation set.
RL-based NAS methods have shown promising results in automatically discovering high-performing neural network architectures. These approaches allow for reducing search time by training on small proxy tasks first, and then transferring the knowledge to the final task. RL-based NAS often achieves competitive performance compared to hand-designed architectures while requiring less manual effort.
However, RL-based NAS still faces challenges such as high computational costs and scalability issues due to the large search space and extensive training requirements. Further exploration and optimization are needed to address these challenges and fully harness the potential of RL-based NAS.
Absolutely, Samantha. One area of current research in NAS is focused on addressing these computational and time-intensive challenges. Researchers are exploring the use of reinforcement learning algorithms to guide the search process and make it more efficient. By using RL, NAS algorithms can explore a larger search space and discover optimal architectures more effectively.
That's right, Theo. The use of reinforcement learning in NAS has been a notable advancement in the field. It employs neural networks as function approximators to estimate the quality of different architectures based on their performance on a specific task. This approach allows for more efficient exploration of the search space and reduces the need for human intervention.
Additionally, there is a growing interest in developing NAS strategies that are transferable across different tasks and datasets. This would greatly reduce the need for repeated architecture searches and save both time and computational resources. Transferable NAS approaches aim to discover architectural principles that generalize well across various domains, resulting in more versatile and adaptable models.
Absolutely, Theo. Transfer learning is one way to achieve this integration of NAS with other techniques. By using pre-trained models or architectures found using other algorithms as starting points for NAS, the search space can be reduced and the search process can be accelerated. This integration allows for a more comprehensive and efficient exploration of the design space.
Another way to integrate NAS with other methodologies is through the use of meta learning. Meta learning involves using the performance of different architectures as an input to guide the search process. By combining NAS with meta learning, researchers can leverage the strengths of each approach and achieve better results in terms of architecture design and model performance.
Absolutely, Theo. The integration of NAS with other machine learning methodologies has shown great potential in enhancing the overall efficiency and effectiveness of architecture design. It allows for a more comprehensive exploration of the design space and leverages the strengths of different techniques to achieve better results.
Moving on to future directions in NAS, researchers are looking into expanding the search space beyond traditional layer-level architectures. They are exploring the inclusion of more complex structures, such as skip connections and attention mechanisms. By expanding the search space, researchers aim to discover new architectural designs that can further improve the performance of deep learning models.
That's right, Theo. The exploration of novel search spaces and network architectures is a critical aspect of NAS. As machine learning tasks become more complex and diverse, it is essential to consider different types of search spaces beyond traditional architectures. This allows researchers to automatically discover new network architectures that can improve the performance of various tasks.
Absolutely, Samantha. NIS provide the systematic way to explore these novel search spaces by incorporating strategies like mutation, crossover, and selection. These techniques allow the model to navigate through the space efficiently and discover architectures that outperform traditional hand-designed ones. Additionally, the exploration of novel architectures is not limited to convolutional neural networks, CNNs, but also extends to other types of networks such as recurrent neural networks, RNNs, and transformers.
That's a great point, Theo. The ability to explore diverse architectures ensures that NAS can be applied across different domains, making it a powerful tool for advancing the field of machine learning. By pushing the boundaries of what is possible in architecture design, NAS opens up new possibilities for innovation and improvement in various domains.
Moving on to ethical considerations and implications of automated architecture design in NIS, it is crucial to address these concerns. One primary concern is the potential bias within the automated design process. Since the model is trained on existing datasets, it might inherit the biases present in those datasets, leading to discriminatory outcomes.
Absolutely, Theo. This potential bias in automated architecture design is especially alarming when designing systems that have a direct impact on people's lives, such as autonomous vehicles or facial recognition systems. It is essential to ensure that proper safeguards and accountability measures are in place to prevent harm and protect individuals.
Another ethical consideration is the lack of transparency and explainability in the decision-making process of NIS. It becomes difficult to understand how and why a certain architecture design was chosen. This lack of transparency raises questions about accountability and responsibility. Who should be held responsible if an automated system makes a wrong decision?
That's right, Theo. The potential job displacement of human designers is also a factor that needs to be taken into account. As NAS automates the architecture design process, it may lead to the displacement of human designers. It is crucial to consider the implications for the workforce and ensure that appropriate measures are in place to support those affected.
Absolutely, Samantha. Addressing these ethical implications and ensuring proper safeguards and accountability measures is crucial for the responsible development and deployment of automated architecture design in NIS.